Okay guys, so what we're doing in 914 is that we are proving right triangles on the coordinate plane. There are two different methods that we could use. We could use the distance formula to show that the sum of the legs squared is equal to the hypotenuse squared, which is the unique quality of a right triangle. If you want to go ahead and jot down what the distance formula is, you can there. This is actually one way that we could do it. I'll show you on a graph another way that we could actually show that a squared plus b squared is equal to c squared. But you guys could go ahead and write down the distance formula because you'd want to use that if you guys did not have a graph and you guys were just given the points. But again, I'll kind of show you two different ways that we can show a squared plus b squared is equal to c squared. The other way that we can prove that a triangle is a right triangle on a coordinate plane is to show that we have two slopes that are opposite reciprocals or two slopes that are perpendicular, which is something that we've discussed in this unit. Perpendicular lines have slopes that are opposite reciprocals of each other. So we'll kind of go over both ways to prove that a right triangle is a right triangle on a coordinate plane. So what we'll kind of do first is, because I do have the coordinates and a graph, I'm going to go ahead and graph triangle ABC. So A is located at 2, 2, B is located at 6, 1, C is at 3, 1, 2, 3, 4, 5, 6. Make sure you guys label. So this was our A, B, C. Go ahead and connect them. So we'll do that first. So once you guys have that graphed, if we want to, we'll go ahead and kind of use what we have already written down here. We'll do it for one of the sides. So if you guys use the distance formula, we could use it first for finding the length of AC. So we're going to need to use the points that we have for A and C to plug into the distance formula. It's not going to matter which one you guys use as your x1, y1, x2, y2, but I'll probably do, let's see, I'll just do my point A as my x1, y1 and point C as my x2, y2. So I'll go ahead and plug all of that in here. So we'll do x2 is 3 minus x1, which is 2, plus, now we'll do y2, which is 6, minus 2 squared. We can kind of start to simplify this a little bit. So inside the radical, 3 minus 2 is 1, 1 squared is 1, 6 minus 2 is 4, 4 squared is 16. So the length of AC is the square root of 17. Okay, can't simplify that any further, so that is what the length of AC is going to be. And just to kind of remind you guys, we were looking for the length of AC, so we had to use, we used the point 2, 2, and we used the point 3, 6 when plugging it into the distance formula. So this is one way that we could do it, again, using the distance formula, or if you guys have the picture already graphed on there, we've talked before about how we could use the Pythagorean theorem to help us in finding the lengths or distances on a graph. So if we were to do that, so we'll use a different method. So we'll use the Pythagorean theorem. We'll draw a right triangle here to help us out with what the side length of CB is. And again, this is just a different method of finding the distance of CB. So we draw a right triangle and we're going to count the dimensions of it. So you have 1, 2, 3. And then this one down here will be 1, 2, 3, 4, 5. So next is I'm looking for the length of CB. So I'll go ahead and put that here. So if I'm using the Pythagorean theorem to help me out with the length of CB, we're going to say that 3 squared plus 5 squared is equal to C squared. You're going to have 9 plus 25, which is 34. So we'll have 34 is equal to C squared. When you square root it, C is going to be equal to the square root of 34. You could simplify if you wanted to, but in the case of this, what we're going to be doing with these side lengths here is we're going to be plugging them back into the Pythagorean theorem, so you don't really need to simplify them because you're just going to kind of undo that simplifying when we plug it back into the Pythagorean theorem. So the last side that we have to look for is side AB. And again, I'm just going to use the Pythagorean theorem because I have my graph here. If you don't want to, then you could use the, okay, sorry, not sure where I just left off, but you could use, if we want to use the distance formula to help us find the length of AB, you could use points A and B and plug them into your distance formula. Does not matter which one you guys used as your x1, y1, x2, y2. Because I already have mine graphed on here, I'm just going to go ahead and draw a right triangle and use the Pythagorean theorem to find that length there. So it looks like the dimensions of my right triangle are 1 and 1, 2, 3, 4. So to find AB, we're going to have 1 squared plus 4 squared is equal to c squared. Well, 1 squared is 1, 4 squared is 16, 1 plus 16 is 17. And then to get c by itself, we'll square root both sides. So the length of AB is also going to be the square root of 17. So now, once you guys have found the lengths of all three sides of triangle ABC, we're going to plug in the, we're going to plug those three into the Pythagorean theorem to show that a squared plus b squared is equal to c squared, and that we do have a right triangle on this coordinate plane. So let's use this color here. So our A and our B are going to be the smaller legs. Your hypotenuse is always going to be the larger. So if we do the square root of 17 squared plus the square root of 17 squared, set that equal to the square root of 34 squared. Whenever you guys square a square root, all we're doing is sort of eliminating that radical sign. So the square root of 17 squared is just 17. So if we double check this, we'll have 17 plus 17 is equal to 34. 17 plus 17 is 34. 34 is equal to 34. So we've just shown that this is a right triangle because your a squared plus b squared is equal to the c squared. Okay, so the other way to see if you have a right triangle is we're trying to see if we have two sides, if two of those lines' slopes are the opposite reciprocals of each other. And I'm going to use AC as an example again. So in this method, we're going to find slopes of all three sides. And there's a couple ways that we could do this. If you do not have a graph and all you guys have is the coordinates, then we can use the slope formula, which is y2 minus y1 over x2 minus x1. So I'll use this for, I'll use slope formula for AC. This is kind of the side that I use the distance formula for. So I'll use it for the slope formula as well, and then I'll show you the other way that we could find slope with our other two sides because we have a graph here. So again, it does not matter which one you guys label as your 1s and 2s. I will, this is going to be for AC, and I already have those points written up here. So my y2 would be 6 minus my y1, which is 2, over 3 minus 2, 6 minus 2 is 4, 3 minus 2 is 1. So the slope of AC is going to be 4, or 4 over 1. These are the same thing. So that was AC. Let's go ahead and we'll just do CB. So with CB, I can, because I have this graphed, then we can actually just count the slope. So for CB, here's my side CB. And the dimensions of my right triangle help me out with that slope. So I'm going up 1, 2, 3, 4, 5, back 1, 2, 3. So my slope for CB would be up 5, back 3, which indicates a negative 5 over 3 slope. So I could have counted this slope because it was graphed for me. I also could have counted AC if I wanted to, but just wanted to kind of refresh your memory on the slope formula. And then lastly is side AB. So for AB, I'll just go ahead and count that one as well. So in order for me to find the slope of AB, you can start with the point up here. You can start with point A or you could start with point B. I tend to always start with the point that's kind of underneath. So to get from B to A, you're going up 1, but then you're going back 1, 2, 3, 4. So this is up 1, back 4, which indicates a negative 1 over 4 slope. If you look at these two here, it appears that AC and AB are perpendicular lines. We know that because their slopes are opposite reciprocals. And we already did prove that this was a right triangle using the first method, but this is just another method that you guys could use instead. So because AC and AB are perpendicular lines, it means that they're creating a right angle. This would also show that you guys have a right triangle on the graph. Okay, so in this other example, if we read, it says that AC is the hypotenuse of a right triangle. Find two ordered pairs that could represent point B in the triangle ABC. So we'll go ahead and graph where A and C are located. A is at 2, up 3. Make sure you label it. And C is at -3, -2. So this is the hypotenuse of your right triangle. This one's actually pretty simple, guys. There are two possibilities for where we could have point B. And if this is a right triangle, this is obviously the hypotenuse of the right triangle. So we need two perpendicular legs. So we need a horizontal and a vertical side. So we could put point B over here, it looks like. So point B could be located at -1, 2, 3, +3. That's one possibility. Other possibility would be to put it down here. This could also be B. Either way, you guys have a right triangle here. You also have one here. So in green over here, this point B would be at 2, -2. 2, -2. So not a whole lot involved on that type of example. Okay, so last one, prove the triangle is a right triangle by using the Pythagorean theorem. Notice there is not a graph provided for this one. So if they're asking you to use the method of, if they're asking you to use the Pythagorean theorem to show it, then you guys are going to have to use the distance formula with these points to figure out the lengths of those sides. And then lastly, you'll plug in the lengths of those sides into the Pythagorean theorem. So the first side we'll look for would be AB. And you can just kind of refer to these points here. We'll call this x1, y1, x2, y2. And you're going to plug it into the distance formula, which we do have written at the top of our paper. It's x2, which is -1, minus x1. So x1 is a -2. So minus a negative would be plus squared. And then your y2 is 1 minus a -3 becomes plus 3 squared. Let's see, I'll simplify this over here. -1 plus 2 squared would be what? 1 squared, which is 1. 1 plus 3 is 4. 4 squared is 16. So this is going to come out to be the square root of 17. So that covers side AB. Now we can find, let's just go ahead and find the length of side BC. So BC, we'll use these as our x1, y1. These as our x2, y2. If you have them switched, it doesn't make a difference. Okay, so for BC, we're going to say 3 minus -1, which is going to be plus 1. And then 0 minus 1 squared. That's going to come out to also be the square root of 17. And then lastly, so you've done AB, side AB, side BC. The last side of the triangle would be side AC. So AC, so for AC, we'll do this as our 1s, this is our 2s. So we'll say 3 minus -2, which is plus 2. And then 0 minus -3 would be plus 3. 3 plus 2 is 5. 5 squared is 25. 0 plus 3 is 3. 3 squared is 9. So 25 plus 9 is going to be the square root of 34. And it just so happens this is the same lengths that we had in our example. To begin with, it won't always, you won't always have square root 17, square root 17, square root 34. It'll be different numbers. So after we've found the lengths of those three sides, you're going to plug it into a squared plus b squared equals c squared. So the square root of 17 squared plus the square root of 17 squared is equal to the square root of 34 squared. When you double check it, Simplify this. 17 plus 17 is equal to 34. Well, 17 plus 17 is 34. 34 is equal to 34.